Welcome back, everybody, to our third installment on Kalman filtering. This time we will be talking about the extended Kalman filter. In the last video, you probably just heard before, we were talking about our linear Kalman filter and when it works and when it doesn't work. Because for the regular Kalman filter, we said we can only use it for our state estimation if our system is linear and if our noise is Gaussian. So why doesn't that work when our noise isn't Gaussian? When we have a state estimator that has non-Gaussian noise, we can't feed something that is a Gaussian, this non-Gaussian noise, and expect it to be correct. So for this, it is very important for the extended Kalman filter that our non-linearity destroys our prediction. So that means for our linear system, this all works fine. But what if our system is not linear? So I'll write down what a linear system could look like for our state description, and then we will look at how that will differ for a nonlinear system. So for a state and our measurement with a linear system, we would write it like this with our different noises, so our sensor noise and our process noise. But this doesn't work. For a nonlinear system, for state x, we would write this as a function of x in our previous step, and u, our input, our previous step, and also our sensor noise again. For our measurements, for the nonlinear system, we would write as a function h for our state at the time k plus our process noise. So when we have a system that looks like this and that is nonlinear, we have two options instead of the linear Kalman filter. So when our system is more complex, we can do two different Kalman filters. We can do the extended Kalman filter, which in short we call EKF, and also the unscanted Kalman filter, which in short we call a UKF. Both are options for calculating a state estimation for nonlinear systems or more complex systems, but both are varying in itself in their complexity. So an unscanted Kalman filter is more complex for the estimation and therefore needs more computational time. As a first step to try and calculate an estimation, we would always try the extended Kalman filter method. So for an extended Kalman filter, the one we will be talking about now, this one, we do try, or with this method, we try to approximate our estimation and also linearize it around our mean and the current prediction value. So for this, we use two options. First, we do a Taylor series expansion, and we also need to calculate the Jacobian matrices J. The Jacobian J we can define as and then the matrix as partial So we have our Jacobian. We will use Taylor series expansion. And for that, we need to calculate two matrices. One's the state transition matrix and the other one, the observation matrix. So at first, we do have F from K, our state transition, like we've already learned in the previous videos. We will use this and calculate it as delta F, delta X, as K minus 1, K minus 1, and U from K. So we're looking at the estimated step and the current input for the state transition. For our observation matrix H, we will be looking at delta H, delta X, at our state K, K minus 1. So those two are important to calculate in the end our estimation. In the next step, we will calculate that estimation again with our 3 steps that we already know. So very important to note for this one is that if our system looks like this and we know what it looks like and understand it very well, we can use the Taylor series expansion. But if we do not know our system or not very well, we do need to use other methods, like for example the Monte Carlo methods, to calculate our estimation. Because if we don't do that, we might not get a very good estimation and have a lot of mistakes in our estimation. All right, so how do we do this for the extended Kalman filter? Again, we will go back to our 3 steps: the prediction, the correction, and the update. First, we start again with our prediction for the current estimation. We do have our state X at K minus 1. For F, our state transition. Q. And also our covariance again, like in the first linear Kalman filter one. Okay. K minus 1 for our regular state transition, and covariance at K minus 1 and K minus 1 at our transposed state transition plus Q. Q again is our process error matrix. So we do have our prediction. Then again, we need to correct this state so that it better fits as an estimation. For this again, we do have a calculation as for S, which we use for notational purposes. We do have plus R. Here again, as before, we have our measurement metrics, H, and R, which is our measurement error. So then again, we can calculate L, which is our Kalman gain. Now again with the covariance. So once we have our Kalman gain, we can again calculate delta x, the difference between our first estimated value and the corrected value, which is our Kalman gain for y at k minus h, our observation matrix for x at k minus 1. So once we have our correction, we can again calculate our update. And for this, we have our new state and k, which is previous state plus the Kalman gain and our delta y. About delta y, we talked last time. This is the residual for the measurement. So then we also need to update our covariance matrix at k, and this again is covariance at k minus 1 minus Kalman gain, or S, and the transposed Kalman gain. These two equations are identical to the linear Kalman filter. Okay, so we now know what to do for our extended Kalman filter. We also need to talk about what we can't do, or when the extended Kalman filter is not ideal. So one thing that we need to pay attention to is that for our extended Kalman filter, if our initial estimation, so the very first estimation step we're taking, is way off, we do have the problem that with each step and each prediction, correction, update, we diverge even further from the correct prediction. So if we start off wrong, this is worse than doing a linear Kalman filtering algorithm. So that's one problem. We also, if our nonlinear model that we have with this, the nonlinearities are very large, the filtering algorithm and the estimation also diverges. So if we have very large nonlinearities, we might need to use the unscanted Kalman filter. Also, second problem, the covariance matrix that we estimate for this, so the P, always, or almost always, underestimates the actual covariance. So what that means for us is, if we underestimate the covariance, then it very quickly becomes inconsistent. So we do need a stabilizing factor or a stabilizing noise, which we do have later in the UKF. But that is very dependent on what you're actually trying to do, if you would use the UKF or stay with the EKF.